Cosmic filaments and voids are the grandest features of the universe. They define the large-scale structure of everything. These features are crucial to understanding how galaxies form and evolve. When we speak of cosmic filaments, we imagine vast thread-like structures. They are woven from dark matter gas and entire galaxies. These threads stretch across immense distances, creating a cosmic web. This web connects the great clusters of galaxies. Filaments are found at the intersections of these large-scale structures. They act as channels for gas and dark matter. They provide the raw material needed for star formation and galaxy growth. Meanwhile, voids are the enormous empty spaces between these filaments. Here, very few galaxies can be found. They can be incredibly vast, spanning hundreds of millions of light-years. Their formation is a subject of ongoing and intense research. The creation of these cosmic structures is thought to be influenced by gravity, specifically the gravitational pull of dark matter. Dark matter makes up a significant portion of the universe's total mass. We cannot see it directly. It does not emit light or interact with normal matter in familiar ways. But as dark matter clumps together under its own gravity, it creates a scaffold. This invisible framework allows visible matter to accumulate. This process eventually leads to the formation of galaxies. Over billions of years, these processes have given rise to the structure we see today. The filaments act like cosmic highways for matter. They guide the flow of gas and stars toward denser regions. The voids represent areas where matter has been largely cleared out. The study of these structures also sheds light on the history of the universe. It tells us about its expansion. The distribution of galaxies within filaments and voids reveals important clues about the rate of cosmic expansion. This expansion has been accelerating due to a mysterious force known as dark energy. This acceleration has profound implications for the future of the universe. It may determine whether it expands forever, slows down, or collapses. Observations from powerful telescopes provide a wealth of data. Surveys like the Sloan Digital Sky Survey map these structures in 3 dimensions. This helps us visualize how they relate to one another across cosmic distances. Moreover, cosmic filaments and voids are not just static features. They can host a variety of phenomena, including vast clouds of hot gas that emit X-rays. This gas is heated to millions of degrees by gravitational interactions. It traces the shape of the web glowing faintly in the dark. Cosmic filaments are massive elongated structures. They contain galaxies, galaxy clusters, gas and dark matter. They stretch across hundreds of millions of light-years, connecting the great clusters in a delicate web-like pattern. These filaments are the very threads of the cosmic web. Galaxies are packed densely along their lengths. Voids, on the other hand, are the vast, nearly empty regions between them. Voids can be incredibly large. They are the largest known structures in the entire universe. In cosmology, these structures are defined through the study of galaxy distribution, using surveys that map the positions of billions of galaxies. Researchers can observe how these structures form and evolve over time. The concept of the cosmic web originated from simulations based on the cold dark matter model. This model suggests that dark matter, though invisible, plays a crucial role. The gravitational pull of dark matter attracts regular matter. This leads to the formation of galaxies and clusters along the filaments. The areas between these structures where gravity's influence is weaker become voids. These are generally low-density regions of space. With significantly fewer galaxies, these filaments are not random arrangements. They form due to the fundamental nature of gravity and the initial conditions of the universe shortly after the Big Bang. As the universe expanded and cooled, small fluctuations in density were magnified. Gravity began pulling matter together, forming the intricate patterns we see today. The study of these structures is essential for understanding the universe's architecture. as well as the evolution of galaxies over billions of years. Interestingly, the study of voids challenges some of our ideas about cosmic evolution. They tend to host a different set of physical processes. Compared to the denser regions of the filaments, for example, galaxies within voids may evolve differently. They experience less interaction with other galaxies. This can lead to unique characteristics and evolutionary paths. The existence of voids also raises questions about the distribution of dark energy, which affects the expansion rate of the universe. Understanding how filaments and voids interact with this mysterious force is a key goal. Cosmic filaments act as the primary scaffolding of cosmic architecture. They are not merely aesthetic features. They have profound implications for our understanding of cosmic evolution. The gravitational pull of these filaments influences the motion of galaxies, guiding them along the filaments as they move through space. This means that galaxies are not randomly scattered. Instead, they tend to cluster along these cosmic highways. This helps to explain the large-scale distribution of galaxies we observe today. Moreover, cosmic filaments are where most of the universe's baryonic matter is found. Baryonic matter is the regular matter of stars, planets, and living beings. This gas can cool and condense to form new stars. The process of star formation is often triggered by interactions within these filaments. As gas flows along the filaments, it can accumulate and create dense regions. These regions eventually collapse under their own gravity, leading to the birth of stars and galaxies. This means that cosmic filaments not only shape the universe's structure, they also play a vital role in the formation of the very objects that populate it. Furthermore, studies using advanced telescopes and simulations have revealed something key. These filaments are dynamic, constantly changing as they evolve. They can merge or split over cosmic timescales. Their properties can vary greatly depending on their age and environment. The interactions between filaments also contribute to the evolution of the cosmic web. They can impact the flow of gas and the formation of structures within it. It is fascinating to think about these immense structures, existing on scales of hundreds of millions of light years. They are interconnected, influencing not just the galaxies they host, but also the cosmic environment around them. In addition, cosmic filaments are essential for understanding the behavior of dark matter. It does not emit light or energy, making it difficult to detect directly. However, its presence can be inferred through its gravitational effects. The filaments provide a map of where this invisible matter resides. Cosmic voids and cosmic filaments play very different roles in the distribution of matter. Cosmic voids are vast, relatively empty spaces. They contain significantly lower densities of matter compared to the universe's average. In contrast, cosmic filaments are the largest known structures. They consist of dense concentrations of matter. They are made up of galaxies, gas, and dark matter, forming long thread-like structures that connect clusters. The density of matter in cosmic filaments is much higher, often exceeding the average density of the universe. They serve as the highways for matter, guiding the formation of galaxies and clusters. The stark contrast between these two structures lies in their formation. Cosmic voids are thought to have formed early in the universe's history, as regions where matter was less densely packed. This allowed for the gravitational collapse of surrounding areas, creating the filaments and clusters we see. This process, known as gravitational instability, leads to the clustering of matter. As a result, cosmic voids become places where galaxies are sparse, and dark energy can have a more pronounced effect, as there is less matter to counteract the expansion of space. On the other hand, cosmic filaments are where the majority of visible matter resides. The gravitational pull within these filaments is strong enough to attract more matter. This contributes to the formation of new galaxies and the growth of existing ones. This dynamic interplay between voids and filaments is crucial. It illustrates how the universe's structure is shaped by gravity and dark matter. Moreover, the study of these structures provides important insights into the overall composition of the universe. Observing the differences in matter density helps astronomers learn about dark matter, which, while invisible, provides the gravitational framework of the cosmos. The existence of cosmic voids also raises intriguing questions about the future, as these areas of low density may expand more rapidly than regions of higher density. This could influence the universe's ultimate fate. Cosmic voids can also reveal information about the early universe. Their sizes and distributions can inform scientists about the initial conditions after the Big Bang. To understand these vast and intricate structures, astronomers employ a variety of techniques. They use different wavelengths of light-advanced technology and statistical methods. One prominent technique is the use of large-scale surveys, conducted with powerful telescopes that capture images over extensive areas. These surveys gather vast amounts of data, allowing scientists to map the distribution of galaxies and other cosmic structures. By analyzing the light emitted from these galaxies, researchers can infer the presence of dark matter and the surrounding cosmic web. That includes filaments connecting galaxy clusters, while also identifying massive voids where galaxies are sparse. Spectroscopy is another vital observational method. It enables astronomers to study the light from distant objects in more detail. By breaking down light into its constituent colors or spectrum, scientists can measure various properties such as redshift. Redshift helps determine how fast an object is moving away from us. It provides insights into the expansion of the universe. This technique also allows researchers to examine the chemical composition of galaxies, which can reveal how cosmic filaments influence star formation and evolution. Gravitational lensing, a phenomenon predicted by Einstein, is also essential. When massive objects lie between us and more distant galaxies, they warp space. This bends the light from those distant galaxies. This bending of light creates distorted images, which can be analyzed to infer the mass and distribution of matter, including the invisible dark matter in cosmic filaments. This technique provides a unique way to visualize the large-scale structure, revealing how filaments and voids are interconnected through gravitational forces. Furthermore, radio astronomy plays a critical role. Large radio telescopes can detect the faint radio emissions from hydrogen gas, which is abundant in cosmic filaments. By mapping these emissions, astronomers can trace the large-scale structure, including how filaments form and evolve over time. This approach complements optical and infrared observations, allowing for a more comprehensive understanding of the universe's architecture. In addition to these techniques, simulations and computer modeling are crucial. They provide insights into the formation and dynamics of cosmic filaments and voids. By comparing observational data with these digital universes, scientists can test their theories about how matter is distributed and how the cosmic web came to be. Cosmologists use these sophisticated techniques to map the distribution of filaments and voids. This is crucial to understanding the large-scale structure and cosmic expansion. One primary method involves large-scale surveys of galaxies. Telescopes capture light from a vast number of galaxies, providing data on their positions and redshifts. Redshift is the shift in light towards the red end of the spectrum. Due to the universe's expansion, this data helps cosmologists determine how fast galaxies are moving away, allowing them to infer distances and map the three-dimensional arrangement. Another important technique is the analysis of the cosmic microwave background radiation, the afterglow of the Big Bang. It provides a snapshot of the universe when it was just 380,000 years old. By studying the tiny temperature fluctuations in this radiation, cosmologists can infer the density variations in the early universe, which eventually led to the formation of filaments and voids. Additionally, gravitational lensing is used to map the distribution of dark matter. It reveals the gravitational influence of unseen structures, helping to identify where the mass of filaments is concentrated. Moreover, simulations play a vital role. By using computational models that simulate the evolution of the universe, scientists can compare their simulations with actual observational data. These simulations take into account various factors, including dark energy and dark matter, allowing cosmologists to predict where filaments and voids should be located. Based on the laws of physics, as technology advances, new observational techniques are emerging, such as using radio waves to study neutral hydrogen, offering even more detailed insights into the cosmic web structure. Collaboration across global networks of observatories has also enhanced the mapping process. The Sloan Digital Sky Survey has provided an extensive catalogue of galaxy positions, while other surveys focus on different wavelengths like infrared or even gravitational waves to gather diverse data. This multi-wavelength approach is crucial. It allows researchers to paint a more comprehensive picture of the universe's architecture, revealing how filaments and voids relate to each other over cosmic distances. The cosmic web is a vast, intricate tapestry of matter. It plays a crucial role in our understanding of the universe's architecture and its evolution over time. This web consists of filaments of galaxies and dark matter, which stretch across the cosmos, connecting clusters and groups of galaxies, and forming a large-scale structure that reveals how the universe is organized. The significance of the cosmic web lies in its ability to provide insights into the distribution of galaxies, the behavior of dark matter, and the dynamics of expansion. As astronomers have discovered, the web-like structure is not random. It follows the principles of gravity and the initial conditions created by the Big Bang. The formation and clustering of galaxies are influenced by the gravitational pull of dark matter, which makes up about 27% of the universe. As we map the cosmic web, we can better understand how galaxies form and evolve, tracing their histories back to the early universe, when tiny fluctuations in density led to the growth of structures. This mapping is facilitated by advanced telescopes and surveys, which have collected vast amounts of data on the positions and movements of galaxies, helping scientists to visualize this immense structure. In doing so, we gain insights into the physics of the universe, including the roles of matter, and dark energy. Dark energy is believed to drive the accelerated expansion of the universe. The cosmic web also helps us understand superclusters and voids. Superclusters are large groups of galaxies that are gravitationally bound, while voids are vast empty spaces between these clusters. Studying these components allows researchers to investigate the anisotropies in the universe and how they relate to cosmic inflation, the rapid expansion that occurred just after the Big Bang. These studies can shed light on the fundamental properties of the universe, such as its overall shape, curvature, and fate, leading to a deeper comprehension of whether the universe is open, closed, or flat. Moreover, the cosmic web is not just about the arrangement of galaxies. It also influences the flow of gas and the formation of new stars. As matter moves along the filaments, it creates conditions for galaxy formation and growth. Understanding this process is key to understanding the cosmic life cycle. Gravity plays a crucial role in shaping the large-scale structure of the universe, and one fascinating aspect of this is the formation of cosmic filaments. These vast thread-like structures form the backbone of the cosmic web. The formation of these filaments begins with the distribution of dark matter. Dark matter interacts through gravity, attracting normal matter like gas and stars. This attraction leads to the clumping of matter in certain regions of space. As these regions accumulate mass, they create gravitational wells, which pull in even more matter, forming dense knots known as galaxy clusters. Over time, the gravitational pull from these clusters influences the surrounding matter, leading to the stretching and alignment of gas and dark matter into long, thin structures, which we observe as cosmic filaments. These filaments can span millions of light years and contain galaxies, gas, and dark matter, creating a vast network that connects clusters of galaxies. The process is driven by the interplay between gravity and the expansion of the universe. Gravitational forces from dense regions attract surrounding material, while the expansion pushes them apart. This balance creates a dynamic environment where matter flows along the filaments toward the densest regions, further enhancing their structure. Additionally, simulations and observations have shown that the cosmic web's shape is influenced by the initial density fluctuations present in the early universe, which were magnified by gravitational forces as the universe expanded. These gravitational forces also help to determine the orientation of these filaments, leading to the formation of various shapes and sizes. Depending on factors like the initial conditions and the distribution of dark matter. Interestingly, these filaments are not just empty space. They often contain a significant amount of baryonic matter, which can cool and collapse to form new stars and galaxies, playing a vital role in cosmic evolution. Furthermore, research has revealed that the environment around these filaments can impact galaxies. Galaxies within filaments experience different gravitational influences compared to those in isolated regions. For instance, galaxies in denser filament regions may have higher rates of star formation due to the plentiful supply of gas, while those in less dense areas might evolve differently, leading to a diverse range of galactic types and structures. As scientists continue to study these fascinating cosmic filaments, they are using advanced observational techniques to probe their secrets. Dark matter, although invisible and elusive, plays a crucial role in shaping the universe and influencing the formation of cosmic structures. Its presence is inferred through gravitational effects on visible matter and the large-scale structure of the universe. Essentially, dark matter acts as a scaffold, providing the necessary gravitational pull that allows ordinary matter like stars and galaxies to come together. Without dark matter, the universe would look very different. Galaxies would likely be unable to form as they do today. The matter we can see, including gas and dust, would lack the gravitational framework. The framework needed to coalesce into stars and planets, leading to a much sparser and less structured universe. Astrophysicists believe that dark matter originated shortly after the Big Bang, when the universe was still dense and hot. As it expanded and cooled, the density of ordinary matter decreased. But dark matter, which interacts primarily through gravity, continued to clump. This clumping formed the early seeds of galaxies, as dark matter halos began to develop. These halos are now thought to be the gravitational wells that attract normal matter, leading to the formation of stars, galaxies, and galaxy clusters over billions of years. In fact, simulations of cosmic evolution show something profound. Without dark matter, the universe would not have formed large-scale structures. Structures like galaxy clusters, which are among the largest known in the universe. Moreover, dark matter influences the rotation of galaxies. As seen in the rotation curves of spiral galaxies, the outer regions of galaxies rotate at speeds that cannot be explained by the visible matter alone. This discrepancy suggests that there is additional mass present, which is attributed to dark matter. The gravitational effects of dark matter also play a role in galaxy collisions and mergers. These events can lead to the growth of galaxies and the formation of new structures, as dark matter contributes to the overall gravitational field that governs these interactions. Interestingly, researchers study the cosmic microwave background radiation, the afterglow of the Big Bang, to understand the distribution of dark matter. Analyzing fluctuations in this radiation helps scientists map out its density in the early universe, revealing how it influenced the distribution of galaxies we observe today. Additionally, gravitational lensing provides further evidence for dark matter. It occurs when light from distant galaxies is bent around massive objects. The amount of bending is greater than what would be expected from visible matter alone, indicating the presence of a substantial amount of unseen mass. In summary, dark matter is a fundamental ingredient in the cosmic recipe. The density of matter in the universe plays a crucial role in shaping the large-scale structure, influencing the formation of filaments and voids. To understand this, we must first consider how matter is distributed. In regions where the density of matter is higher, gravity pulls matter together, causing it to clump and form structures like galaxies and galaxy clusters. These dense regions create gravitational wells that attract surrounding matter, leading to the formation of filaments. The density of matter affects the gravitational force exerted in these regions, meaning that the higher the density, the stronger the attraction, resulting in more pronounced filaments. Conversely, in areas where the density of matter is low, we find large voids. These are vast, empty spaces that can be millions of light years across. These voids represent the regions of the universe with a significant lack of galaxies. The formation of voids occurs as matter clumps together in denser areas, leaving behind these large, underdense regions. As the universe expands, the dynamics of matter distribution continue to evolve, with gravitational interactions leading to the growth of filaments on one hand, and the further expansion and isolation of voids on the other. The interplay between dark matter and baryonic matter also affects this process. Dark matter does not interact with electromagnetic forces, meaning it does not emit light and is invisible. However, it exerts a strong gravitational influence, helping to shape the structure of the cosmic web. As dark matter clumps together, it forms a scaffold, upon which visible matter like stars and galaxies can coalesce. This means that the distribution of dark matter is heavily linked to the formation of both filaments and voids. Observations from large-scale surveys have provided valuable insights into the density fluctuations of the universe. These surveys have revealed a pattern where regions of higher density are organized into a web-like structure, with filaments acting as highways for galaxies, while voids remain as vast empty spaces. The density of matter directly influences the gravitational forces at play, dictating how matter moves and clusters over cosmic time. Cosmologists often use computer simulations to model the evolution of the universe, showing how variations in matter density lead to the structures we observe. The universe as we observe it today is a vast and intricate tapestry, filled with galaxies, clusters, and immense voids, all connected by cosmic filaments. To understand how these structures formed, we must delve into the primary theories that explain the initial conditions of the universe. One of the most widely accepted theories is the Big Bang theory. It posits that the universe began as an extremely hot and dense point, approximately 13.8 billion years ago. As it expanded, it cooled, leading to the formation of fundamental particles. Over time, these gases clumped together under the influence of gravity, creating the first stars and galaxies, which then began to form larger structures. Another important concept is the role of cosmic inflation, a theory proposed by Alan Guth in the early 1980s. Inflation suggests that within the first moments after the Big Bang, the universe underwent a rapid exponential expansion, smoothing out any unevenness in the distribution of matter and energy. This initial expansion set the stage for the large-scale structure we see today, as tiny quantum fluctuations in the density of matter during inflation were stretched to cosmic scales, leading to areas of slightly higher and lower density. These variations became the seeds for future structures, with regions of higher density eventually collapsing under gravity to form filaments, while the lower density areas became the vast voids. Additionally, the concept of dark matter plays a vital role. Dark matter interacts with regular matter through gravity, but does not emit light, making it invisible. Its presence influences the motion of galaxies and the formation of large-scale structures, acting as a scaffolding around which visible matter can cluster. Simulations of the universe's evolution show that dark matter tends to clump together first, forming a web-like structure that dictates where galaxies and clusters will eventually form, creating the filaments that connect them, while the regions between these filaments remain relatively empty, leading to the formation of voids. Moreover, the role of baryonic matter cannot be overlooked. This includes all the elements that make up stars, planets, and living organisms. When galaxies form within the dark matter filaments, they often draw in surrounding gas, fueling their growth. Inflation theory plays a vital role in understanding the large-scale structure of the cosmos. According to this theory, during the first few moments after the Big Bang, the universe underwent exponential growth, expanding faster than the speed of light. This expansion smoothed out any initial irregularities, but quantum fluctuations, tiny variations in density, were stretched across vast distances. These fluctuations, though small, became the seeds for the future structure of the universe. As the universe continued to expand and cool, regions with slightly higher density began to attract matter, while lower density regions began to form voids. Over billions of years, these initially small fluctuations led to gravitational collapse, forming the large-scale structures we observe today, including cosmic filaments. These filaments are vast, thread-like structures composed of galaxies, gas, and dark matter. They connect clusters of galaxies, creating a web-like appearance. The voids, on the other hand, are the vast empty spaces between these filaments. The interplay between the expansion of the universe gravity and dark matter is essential. For this structure to emerge, the cosmic web provides insights into the evolution of the universe. Researchers have found that simulations and observations match the predictions made by inflation theory, indicating that the early rapid expansion influenced the way matter clumped together. The existence of cosmic filaments and voids offers a glimpse into the universe's history and highlights the role of inflation in shaping the cosmos. As scientists continue to study the cosmic web, they are also exploring how these structures influence the behavior and formation of galaxies. For example, filaments act as highways for gas, allowing it to flow into galaxies, fueling their formation and growth. Meanwhile, the voids can affect the motion of galaxies, as galaxies within filaments tend to move toward each other, while those in voids experience a different gravitational influence. This dynamic interaction is crucial for understanding galaxy evolution. The connection between inflation theory and cosmic structure also extends to dark energy, which is believed to be responsible for the accelerated expansion of the universe. As the universe expands, the distribution of matter changes, influencing the formation and growth of the cosmic web. Baryonic matter, which consists of protons, neutrons, and electrons, plays a crucial role in the formation of cosmic filaments. These filaments, composed of dark matter gas and galaxies, are fundamental in shaping the large-scale structure of the cosmos. The baryonic matter, primarily in the form of hydrogen and helium gas, contributes significantly to the density fluctuations in the early universe. As the universe expanded and cooled after the Big Bang, small density variations allowed areas with slightly more baryonic matter to attract surrounding matter. Due to gravitational forces, this gravitational attraction is essential as it pulls in more baryonic and dark matter, leading to the formation of higher density regions that eventually evolve into filaments. As these filaments form, baryonic matter also influences the behavior of gas within them. The gas becomes denser along the filaments, leading to the formation of galaxies and galaxy clusters through gravitational collapse. Over time, the baryonic matter in these regions can cool and condense, which allows for star formation and the creation of complex structures. In this way, baryonic matter not only contributes to the initial formation of filaments, but also plays a vital role in their ongoing evolution as stars and galaxies form and interact within them. Moreover, baryonic matter is instrumental in the process of cosmic feedback, where energy from star formation and supernovae can redistribute matter and energy back into the surrounding environment. This feedback helps regulate the growth of galaxies and can influence the temperature and density of the gas in filaments, further affecting their evolution. Additionally, the presence of baryonic matter in cosmic filaments affects gravitational lensing. The baryonic components add to the overall mass of the filaments, which bends the light around them, allowing astronomers to study the distribution of both baryonic and dark matter. In summary, baryonic matter is essential in the formation and evolution of cosmic filaments, influencing everything from the initial density fluctuations in the early universe to the complex processes that lead to the formation of galaxies and stars, showcasing the interconnectedness of matter in the cosmos. Cosmic filaments play a crucial role in the formation and evolution of galaxies. These filaments connect clusters of galaxies forming the cosmic web. As matter flows along these filaments, it contributes to the gravitational pull that helps in the formation of galaxies. When gas falls into these filaments, it tends to cool and condense, leading to the formation of stars and galaxies. This process is not instantaneous. It occurs over billions of years, with the filaments acting as highways for the infall of matter. The density of the cosmic filaments affects how galaxies evolve over time. Within denser parts of these filaments, galaxies can merge more frequently, which can lead to larger and more complex galactic structures. Conversely, in regions where the filament density is lower, galaxies may evolve more slowly, often becoming isolated. This variation in density leads to the diversity we observe in galaxy types, including spiral, elliptical, and irregular galaxies. Moreover, cosmic filaments influence the rate of star formation within galaxies. Regions along the filaments can become hotbeds of star formation due to the inflow of gas, while areas further away may see reduced star formation activity. Additionally, cosmic filaments can impact the distribution of dark matter, a critical component of galaxy formation. Dark matter is thought to clump along these filaments, creating gravitational wells that can trap baryonic matter, the ordinary matter that forms stars and planets. This clumping of dark matter not only helps in the formation of individual galaxies, it also plays a significant role in the formation of galaxy clusters, where multiple galaxies gather together. As galaxies move through these filaments, their interactions can lead to various evolutionary paths, including collisions and mergers. Such mergers can trigger bursts of star formation, altering the galaxy's structure and the dynamics of its stars. Furthermore, cosmic filaments can also influence the large-scale structure of the universe. The way in which galaxies are distributed across the cosmic web has implications for our understanding of the universe's expansion and the nature of dark energy. Observations of the cosmic web and its filaments provide valuable insights into the history of the universe, helping to map out how galaxies have moved and evolved over time. In essence, cosmic filaments are the nurseries and highways of the cosmos. Cosmic voids, those vast empty regions of space, play a significant role in our understanding of dark energy, the mysterious force driving the accelerated expansion of the universe. When we look at the structure of the universe, we see a complex web of galaxies and galaxy clusters interconnected by filaments of dark matter, with these voids acting as the spaces in between. almost like the holes in a cosmic sponge. The existence of these voids suggests that matter is distributed unevenly, which raises intriguing questions about how dark energy interacts with the universe's structure. One key implication is that voids might influence the expansion rate of the universe, because in these low-density regions gravity is weaker. This could lead to a different behavior in the dynamics of cosmic expansion. Researchers have observed that galaxies located within voids tend to move faster than those in denser regions, a phenomenon that can be partially attributed to the effects of dark energy. This accelerated movement within voids provides valuable insights, hinting that dark energy might have a varying influence depending on local density. This challenges our traditional understanding of this enigmatic force as being uniform across space. Moreover, studying cosmic voids helps scientists test various cosmological models, including those that incorporate dark energy. By analyzing how light from distant galaxies is affected as it travels through these voids, researchers can gather data on the universe's geometry and expansion history. This has led to the discovery that voids can also affect the cosmic microwave background radiation. By altering the temperature fluctuations we observe, this interaction further solidifies the connection between cosmic voids and dark energy, suggesting that voids could serve as natural laboratories for exploring the characteristics of dark energy and its role in cosmic evolution. In addition, voids may provide clues about the nature of dark energy itself. Some theories propose that dark energy could be an effect of the large-scale structure, rather than a constant force. The unique conditions within voids, which are largely devoid of matter, might reveal how dark energy behaves in different environments, potentially leading to new insights into whether it is a true cosmological constant, or if it varies with time or space, as suggested by alternative models. Researchers are also utilizing simulations and observations of voids to refine their understanding of dark energy's properties. By studying how voids evolve over time, scientists can constrain these models. Simulations of the universe, or cosmological simulations, play a crucial role in helping researchers understand the large-scale structure of the cosmos, including the formation of filaments and voids. These simulations use powerful computers to model the dynamics of matter and energy. Based on the laws of physics, particularly gravity and hydrodynamics, the universe is not uniformly distributed. Instead, it has a fascinating structure characterized by vast, empty regions called voids, interspersed with dense thread-like structures known as filaments. By creating detailed simulations, scientists can visualize how matter clumps together under the influence of gravity, forming these intricate patterns over time. These simulations often start with a homogeneous distribution of matter, mimicking the conditions of the early universe, and evolve it according to known physics, tracking how regions of higher density attract more matter, while lower density regions become voids. This process allows researchers to observe how small fluctuations can grow into the large-scale structures we see today, revealing how filaments connect clusters of galaxies and how voids form between these structures. Furthermore, simulations provide insights into the role of dark matter, which is believed to make up about 27% of the universe. Dark matter's gravitational effects shape the universe's structure. By incorporating dark matter into simulations, researchers can study how it influences the formation of filaments and voids, offering a better understanding of how galaxies are distributed. With these simulations, scientists can also test various cosmological models, comparing the output of simulations with observations from telescopes to validate or refine our understanding of the cosmos. Moreover, simulations allow researchers to explore different scenarios, such as varying the amount of dark energy or changing the initial conditions. This flexibility helps in understanding how different factors contribute to the current structure. For example, they can simulate the effects of increased dark energy and see how that influences the distribution of filaments and voids over billions of years. By comparing these simulations with actual observational data, scientists can refine their models and develop a deeper understanding of the universe's history, leading to insights into how galaxies form and evolve. When exploring the structure of the universe, one of the most fascinating aspects is how cosmic filaments and voids form and evolve. To model the growth of these cosmic structures, several critical parameters come into play. One of the key parameters is the initial density fluctuations in the early universe. These fluctuations emerged from quantum fluctuations during the inflationary period. They set the stage for how matter would clump together over billions of years. Another important factor is the influence of dark matter, which makes up about 27% of the universe's total mass energy content. Dark matter's gravitational effects play a significant role in shaping the cosmic web, as it provides the gravitational scaffolding around which baryonic matter gathers. The interaction between dark matter and baryonic matter is crucial. In understanding how filaments form, as dark matter halos act as gravitational wells that attract gas and dust. The expansion rate of the universe, described by the Hubble constant, also affects the growth. As the universe expands, the rate at which filaments and voids evolve can be influenced. In particular, the interplay between expansion and gravitational attraction leads to the formation of voids. As matter is drawn into the denser filaments, temperature and pressure conditions in the intergalactic medium are additionally important. The gas in filaments can be affected by shock waves from supernovae and the thermal history of the universe itself. These factors can determine how gas behaves, how it cools, and how efficiently it can collapse to form stars and galaxies. The role of cosmic rays and magnetic fields also cannot be overlooked. Cosmic rays can affect the dynamics of gas in filaments, while magnetic fields can influence the motion of charged particles, impacting the processes that lead to structure formation. Lastly, the scale of simulations used to model these structures is critical. Large-scale cosmological simulations must incorporate multiple scales of structure, from the smallest dark matter halos to the largest superclusters. To accurately capture the complexity of the cosmic web, cosmic filaments play a significant role in the motion of galaxies within them. These filaments form part of the cosmic web, which is essentially the scaffolding of the universe, consisting of clusters, groups, and voids interconnected through these long strands. As galaxies form and evolve, they often find themselves within these filaments, which act like highways guiding their movements. The gravitational pull of the dense regions within these filaments can attract nearby galaxies, causing them to move toward the filaments. This attraction is not just a simple pull, but a complex interaction, where gravitational forces from both the filament and the galaxies create a dynamic environment. As galaxies travel along these cosmic highways, they can experience changes in velocity and direction, influenced by the gravitational forces exerted by the matter in the filaments. The density of the filament can also affect the rate at which galaxies merge or interact, contributing to the growth of larger galactic structures. In densely populated regions of filaments, galaxies may frequently collide and merge, leading to the formation of larger galaxies, which can then become central hubs in clusters. Conversely, in less dense areas, galaxies may travel more freely, experiencing fewer interactions. Additionally, the cosmic filaments themselves are not static. They can evolve over time. Due to the ongoing processes of cosmic expansion and gravitational interactions, this means that the paths that galaxies take can change, as filaments can shift and reorganize, creating new routes for galaxies to follow. This dynamic nature can lead to interesting phenomena, such as the formation of galaxy clusters where many galaxies congregate. resulting in a complex interplay of gravitational forces. Moreover, studies using advanced simulations and observations have shown something key. The distribution of galaxies within these filaments is not random, but follows a specific pattern, influenced by the underlying dark matter distribution. This means that galaxies tend to be found along the edges of filaments, where the gravitational pull is stronger, while the regions in between may host fewer galaxies. This arrangement helps to explain why we observe galaxies in clusters and groups, often aligned along these cosmic threads. The impact of cosmic filaments extends beyond just the motion of individual galaxies. They also affect the large-scale structure and evolution of the entire universe. Cosmic voids play a fascinating role in shaping the cosmic microwave background radiation. The CMB is a relic of the early universe, a faint glow that fills the cosmos. It originated about 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine, allowing photons to travel freely. Now, when we consider the influence of cosmic voids, these regions are not completely empty. They contain a lower density of matter compared to the surrounding areas. This difference in density affects the way light, specifically the CMB photons, interacts. As light travels through space, it can be influenced by gravitational fields. In regions of higher density like galaxy clusters, gravity can bend the path of light, a phenomenon known as gravitational lensing. Conversely, in cosmic voids, the gravitational influence is weaker, which means that the CMB photons passing through these regions experience less bending. This lack of interaction can lead to a slight change in the temperature and polarization of the CMB. As it moves through these less dense areas, voids can create temperature variations in the CMB, leading to the presence of cold spots, regions where the CMB appears slightly cooler than other areas. These cold spots can be traced back to the effects of cosmic voids, as they represent areas where there are fewer structures to contribute to the overall energy density. Moreover, cosmic voids can also impact the large-scale structure of the universe. The way that matter is distributed influences the gravitational wells that form, which in turn affects how CMB photons travel. In regions where there are voids, the gravitational pull is not as strong, which leads to less clustering of matter. This difference in clustering can produce distinct patterns in the CMB that scientists can observe and analyze. The existence of these voids is an important factor in our understanding of the universe, as they represent a significant component of the cosmic web. In addition, the presence of voids can give insights into the nature of dark energy and dark matter. The way voids evolve over time can shed light on the dynamics of the universe, helping astronomers to refine their models of cosmic evolution. Cosmic filaments and voids have been studied extensively, and a variety of evidence supports their existence. First observations from large-scale galaxy surveys have allowed astronomers to map the distribution of galaxies across vast regions of space. These surveys reveal a web-like structure where galaxies are not evenly distributed, but instead they cluster along thin, elongated filaments, forming what is often referred to as the cosmic web. This web has vast empty spaces or voids, which can contain very few galaxies. Moreover, computer simulations of cosmic evolution predict the formation of these structures. When researchers run simulations to model how matter evolves over time, the results show that gravity pulls matter together into dense regions, creating filaments, while other areas become less dense, forming voids. These simulations match well with the actual observations from telescopes, providing strong support for the existence of these structures. Additionally, gravitational lensing has provided further evidence. By observing how light from distant galaxies is distorted by the gravitational fields, scientists can map the distribution of dark matter and see where the filaments are located. This method has confirmed that these filaments are indeed present, and that they contain significant amounts of mass. Another piece of evidence comes from the cosmic microwave background radiation. Analyzing the temperature fluctuations in this radiation helps astronomers understand the density variations in the early universe. These fluctuations eventually led to the formation of cosmic filaments and voids, as denser régions attracted more matter, while less dense régions became voids. Astronomers also use galaxy redshift surveys, which measure how light from distant galaxies shifts due to the expansion of the universe. The redshift data reveal how galaxies are distributed over time and show the large-scale structure of the universe, supporting the idea of cosmic filaments and voids. As galaxies move apart, their distribution outlines the large-scale structure, reinforcing the existence of these massive formations. In summary, the evidence comes from a combination of galaxy surveys, simulations, and gravitational lensing, all pointing to a universe woven into a magnificent cosmic web. Cosmic filaments and voids are fascinating structures that play a crucial role in determining how galaxies are distributed across space. Imagine the universe as a web, with galaxies being like beads strung along the threads of this web, while the gaps in between represent the voids. Cosmic filaments are large-scale structures made up of dark matter gas and galaxies, forming the backbone of the cosmic web. They can stretch for hundreds of millions of light years, connecting clusters of galaxies and serving as highways for the movement of galaxies through space. These filaments are fundamental to understanding the cosmic web. On the other hand, voids are vast, nearly empty regions where very few galaxies are found. They can be incredibly large. The existence of these voids indicates that matter in the universe is not evenly distributed. They provide insight into how galaxies cluster together in certain areas, while leaving other regions largely devoid of galaxies. The interplay between cosmic filaments and voids helps to explain the observed large-scale structure, as the gravitational pull of the filaments attracts matter, causing galaxies to clump together, while the voids serve as areas of lower density. This distribution of galaxies is not random. Rather, it is a result of the underlying physics of gravity and the expansion of the universe. Observations from telescopes have mapped out these filaments and voids, revealing a complex and beautiful structure that reflects the history of the universe's formation and evolution. Moreover, simulations of cosmic evolution have shown how these structures formed over billions of years, influenced by the initial conditions of the universe, such as fluctuations in the density of matter shortly after the Big Bang. These simulations help scientists understand how galaxies have moved and interacted, further emphasizing the importance of cosmic filaments and voids in the cosmic landscape. Understanding the relationship between these structures and galaxy distribution is essential for piecing together the mysteries of dark matter and galaxy formation. As researchers continue to study these cosmic phenomena, they gain deeper insights into not just where galaxies are, but also how they came to be and how they might evolve in the future. In the fascinating realm of cosmology, the formation of voids presents a captivating area of study. Small voids and large voids, while both are regions of low density, have different origins. Small voids, often less than a few million light-years in diameter, tend to form as a result of the gravitational interplay between galaxies and dark matter. As galaxies move and interact, they can create areas of lower density, where the gravitational pull is not strong enough to attract new matter, leading to the formation of relatively small voids. These voids can emerge from the processes of galaxy clustering, where galaxies gravitate towards each other, leaving behind regions that are relatively empty. On the other hand, large voids can stretch across tens of millions of light years. They are believed to be the product of more extensive and complex processes. These larger voids often result from the evolution of the universe on a grand scale. where the distribution of dark matter and normal matter has changed over billions of years. Large voids may form during epochs in cosmic history when matter began to clump together, leading to the formation of massive structures such as galaxy clusters, while simultaneously creating vast underdense regions. As the universe expands, these large voids become more pronounced, as the matter within them continues to be pulled into denser areas, further reducing the number of galaxies in those vast spaces. Another key difference lies in the timing of their formation. Small voids can form relatively quickly, often in the early stages of galaxy formation, while large voids require a longer period of cosmic evolution, developing over billions of years as structures grow. Additionally, the environment surrounding these voids also plays a significant role. Small voids might be found in denser areas of the universe, surrounded by clusters of galaxies, whereas large voids are typically located in more isolated regions, often serving as the backdrop for intricate cosmic web structures. The physics involved in the formation of these voids is also influenced by dark energy, which drives the accelerated expansion of the universe. This expansion can affect the dynamics of both small and large voids, as they respond differently to the stretching and growth of the universe. The age of the universe during filament formation plays a crucial role in determining the structure of these cosmic filaments. When we talk about filaments, we're referring to some of the largest structures, often stretching hundreds of millions of light years across. The formation of these filaments is influenced by the expansion of the universe, the gravitational forces at play, and the distribution of matter, all of which change over time. Initially, when the universe was younger, it was denser and more chaotic, with more clumps of matter forming due to gravitational attraction. As the universe aged, it began to expand, and the distribution of matter became more structured, leading to the creation of the cosmic web. In the early universe, filaments formed as matter began to clump together under gravity. The density and temperature of the universe impacted how quickly these clumps could form. The age of the universe at the time of filament formation also influences their density, as younger filaments tend to have a higher density of dark matter and gas. This density affects the gravitational pull within the filaments, influencing star formation and the evolution of galaxies within these structures. As time goes on, the filaments evolve. Their structure can be affected by the expansion of the universe, which stretches these filaments and can even cause them to become less dense. The interplay between the age of the universe and the structure of filaments leads to a dynamic environment where galaxies can merge and interact, further shaping the cosmic landscape. Additionally, the cosmic microwave background radiation provides a snapshot of the early universe, allowing scientists to understand the conditions under which these filaments formed and how they have changed over time. By studying the age of the universe at various points in its history, researchers can gain insights into the processes that led to the formation of filaments, including the role of dark energy and cosmic inflation. This knowledge helps astronomers piece together the timeline of the universe's development, illustrating how the structures we see today were influenced by the conditions present during their formation. Understanding this relationship not only gives us a clearer picture of the cosmic web, but also sheds light on the fundamental forces that govern the universe's evolution. Cosmic filaments, the vast structures that make up the universe's web-like arrangement, have been studied through several major observational surveys that have deepened our understanding of their formation and role in the cosmos. One of the most significant surveys is the Sloan Digital Sky Survey, commonly known as SDSS, which has mapped millions of galaxies and provided a wealth of data on the large-scale structure of the universe. This survey started in 2000 and utilized a dedicated 2.5-meter telescope at Apache Point Observatory, capturing detailed images of the sky. and allowing astronomers to trace the distribution of galaxies, which reveal the intricate patterns of cosmic filaments. Another influential survey is the 2-degree Field Galaxy Redshift Survey, which was conducted in the early 2000s in Australia. It focused on measuring the redshifts of over 200,000 galaxies, creating a 3-dimensional map that helped astronomers visualize the cosmic web and identify filaments connecting clusters of galaxies. The results from this survey have been crucial in confirming the existence of these structures. The Wiggle-Z Dark Energy Survey, which ran from 2009 to 2016, also made significant contributions. By focusing on a smaller yet densely populated region, it used a multi-object spectrograph to obtain redshifts for approximately 250,000 galaxies. Its data have helped reveal the growth of cosmic structure over time, highlighting how filaments evolve and interact with dark energy. The Baryon Oscillation Spectroscopic Survey, or BOSS, is another key survey, part of SDSS-3. BOSS aimed to measure the distribution of galaxies to understand the effects of baryon acoustic oscillations. By studying the distribution of galaxies and their clustering, BOSS has provided insights into how filaments serve as highways for galaxies, influencing their movements and interactions. More recently, the Hypersoo PrimeCam survey conducted in Japan has been exploring the cosmic web in unprecedented detail, revealing new filaments and structures through its wide field of view. This survey has utilized advanced technology to capture images of large areas of the sky, and its findings are expected to enhance our understanding of how filaments connect to dark matter. Additionally, the European Space Agency's Euclid mission, set to launch in the near future, aims to shed light on dark energy and dark matter with a focus on large-scale structure. Cosmic filaments and voids are crucial in understanding the hierarchical model of galaxy formation, which describes how smaller structures merge to form larger ones over time, creating the complex web of the universe we observe today. This cosmic web is composed of vast thread-like structures known as filaments, which are rich in dark matter and galaxies, while the voids are the relatively empty spaces between these filaments. The existence of these filaments is a direct consequence of gravitational forces. In the early universe, where small density fluctuations began to gravitationally attract surrounding matter. As these fluctuations grew, they formed the seeds for the larger structures that would become the universe's galaxies and galaxy clusters. In the hierarchical model, the process of galaxy formation starts with small perturbations that evolve into larger and larger structures. The filaments serve as the highways for matter, guiding gas and dark matter into regions where galaxies can form. As galaxies move along these filaments, they can collide and merge, leading to the formation of larger galaxies. This means that the filaments are not just passive structures, but rather dynamic environments where galaxies interact and evolve. Moreover, the voids act as the backdrop for this activity, creating a contrast that enhances our understanding of galaxy distribution. As galaxies tend to cluster along the filaments while avoiding the voids, this distribution of galaxies within the cosmic web supports the hierarchical model, as it shows how smaller systems can grow through mergers and accretion, leading to the formation of larger galaxies over cosmic time. Observations from telescopes have mapped out these cosmic filaments and voids, providing evidence that aligns with simulations of hierarchical galaxy formation. These simulations illustrate how the universe's structure emerges from the gravitational interplay of dark matter and baryonic matter, leading to the intricate pattern of galaxies we see today. Furthermore, studies of the cosmic microwave background radiation revealed something important. The seeds of structure formation initiated during the inflationary period set the stage for the emergence of these filaments and voids. As the universe expanded and cooled, the fluctuations in density created the framework. within which galaxies and clusters would eventually form. Therefore, the relationship between cosmic filaments, voids, and the hierarchical model is foundational to our understanding of the universe's evolution. Cosmic filaments play a significant role in shaping the intergalactic medium, the matter that exists in the space between galaxies. These filaments are composed mostly of dark matter along with gas and galaxies. They are crucial for the formation and evolution of the universe. As the universe expands, these filaments provide a framework that influences how galaxies are distributed in space, creating an intricate tapestry that connects clusters of galaxies. Their gravitational pull affects the motion of galaxies within them. When we delve into the intergalactic medium, we find that it is primarily made up of hot ionized gas, often referred to as the warm-hot intergalactic medium. The presence of cosmic filaments has a direct impact on this medium, as they act as conduits for gas flows, enabling the transfer of materials from one region of the universe to another. This movement is essential for the recycling of gas, which can lead to star formation in galaxies. Additionally, the filaments influence the temperature and density of the intergalactic medium, as the gravitational forces exerted by these structures can compress gas, leading to increased temperatures and changes in density. Furthermore, cosmic filaments can also affect the ionization state of the intergalactic medium. The interactions between the hot gas within the filaments and the surrounding medium can lead to processes that ionize the gas, affecting its overall composition. For instance, as galaxies form and evolve along these filaments, they can expel material, which includes metals and other elements, enriching the intergalactic medium over time. This enrichment is crucial, as it influences the chemical evolution of galaxies and the formation of new stars. Moreover, cosmic filaments are thought to play a role in cosmic structure formation itself, as they help to regulate the flow of dark matter and baryonic matter. This regulation can lead to the formation of large-scale structures like galaxy clusters, which are the largest gravitationally bound systems in the universe. The interactions within and along these filaments can also lead to shock waves that heat the intergalactic medium, resulting in various observable phenomena, including X-ray emissions from hot gas which astronomers can detect. In essence, the impact of cosmic filaments on the intergalactic medium is multifaceted, influencing everything from gas flows and temperature to chemical composition and cosmic evolution. Cosmic voids influence not just the arrangement of galaxies, but also their brightness. These voids can be thought of as the large-scale, underpopulated regions in the cosmos, where the density of matter is significantly lower. This lower density affects how galaxies form and evolve, leading to interesting consequences for their luminosity and distribution. In these cosmic voids, the gravitational pull is weaker, which means that galaxies experience less attraction from other nearby galaxies. This can lead to a reduced rate of galaxy formation, as there are fewer resources available such as gas and dust, which are essential for forming new stars. Consequently, galaxies within voids tend to be less luminous than those found in denser regions, where gravitational interactions can trigger star formation and enhance brightness. Furthermore, the distribution of galaxies within these voids is not uniform. While one might expect a random scattering of galaxies, studies have shown that they often form in filaments or walls at the edges of voids, where the density slightly increases. This phenomenon occurs because galaxies tend to cluster around regions where there is enough matter to provide the necessary gravitational influence. In the center of the voids, galaxies are sparsely distributed, with large distances between them, which can hinder their interactions and reduce opportunities for mergers, an important process that can significantly boost luminosity. Moreover, the cosmic microwave background radiation also interacts with cosmic voids. The voids are colder than their denser counterparts, which influences the way light travels through these regions. The light from distant galaxies can be stretched or dimmed as it passes through these voids, an effect known as gravitational lensing. This can further affect our observations, making galaxies appear less luminous than they actually are. Depending on their position relative to the void, the study of cosmic voids is still a relatively young field, but researchers have been utilizing advanced techniques such as computer simulations and deep sky surveys to understand how these empty spaces affect the evolution of galaxies over cosmic time. Observations suggest that void galaxies can exhibit different properties, such as lower star formation rates and different chemical compositions, which might lead to a unique evolutionary path compared to their counterparts in denser regions. Interestingly, as the universe expands, the voids themselves can grow larger, potentially leading to even more dramatic effects on the galaxies within them. Cosmic filaments play a crucial role in the flow of gas and dark matter. These filaments, composed of dark matter and gas, create a vast network that connects galaxies and galaxy clusters, influencing the overall structure and evolution of the universe. As matter in the universe expands, cosmic filaments act like a cosmic web, guiding the flow of gas towards galaxies, facilitating the process of star formation and ensuring that galaxies have the necessary material to grow over time. The gas in these filaments is primarily hydrogen, which provides the raw material for new stars. Through a process called gravitational attraction, the filaments draw in surrounding gas and dark matter, pulling them into denser regions where they can eventually collapse to form stars and galaxies. The role of cosmic filaments is particularly important when it comes to understanding dark matter, which still has a profound impact on the universe's structure. Dark matter forms a web-like structure that outlines the filaments, creating gravitational wells that further attract ordinary matter. This interaction between dark matter and gas is essential for the formation of galaxies, as the gravitational pull of dark matter helps to hold galaxies together, while the gas provides the necessary fuel for star formation. Observations from large-scale surveys have revealed that these filaments are not evenly distributed. Instead, they tend to be denser in certain regions, leading to a non-uniform distribution of galaxies across the universe. Moreover, as gas flows along these cosmic filaments, it can condense and cool, which promotes the process of star formation. This means that regions along the filaments can become hotbeds of new stars, leading to the creation of new galaxies over time. The dynamics of this gas flow can also trigger various astrophysical phenomena, including the formation of massive galaxy clusters, which are some of the largest structures in the universe. The interplay between the flow of gas and dark matter in cosmic filaments is a complex but fascinating subject, revealing how interconnected everything in the universe truly is. Research utilizing advanced simulations and observations is continually improving our understanding of these grand cosmic processes. Cosmological simulations are powerful tools that researchers use to study the large-scale structure of the universe, including the fascinating cosmic filaments. These filaments consist of dark matter and gas. They serve as the highways for galaxy formation and evolution. By creating detailed computer models of the universe, scientists can simulate how matter behaves under the influence of gravity. Over billions of years, these simulations allow researchers to explore the dynamics of cosmic filaments, including their formation, growth, and interaction with surrounding matter. In these simulations, the initial conditions of the universe are set based on observations from the cosmic microwave background and galaxy surveys. As the simulation progresses, gravitational forces cause matter to clump together, forming structures like galaxy clusters and filaments. Researchers can track how these filaments evolve over time and how their properties, such as density and temperature, change as they interact with other structures in the universe. One of the key aspects of these simulations is their ability to predict the properties of filaments. Researchers can examine how different parameters influence their characteristics. For instance, simulations show how the density of matter within a filament affects its ability to accrete gas, which is essential for the formation of galaxies. By analyzing the outcomes of various scenarios, scientists can gain insights into the conditions that lead to the observed structures. Moreover, cosmological simulations can also help in understanding the role of filaments in the larger context of galaxy formation. As galaxies are often found at the intersections of these filaments, the simulations can reveal how the flow of gas and dark matter along these structures influences the growth and evolution of galaxies. They can also help predict how galaxies might behave in the future and how they might respond to various cosmic phenomena. Additionally, these simulations are validated by comparing their predictions with observational data. This comparison helps ensure that the simulations accurately reflect the real universe, allowing researchers to refine their models. The advancements in computational power and numerical techniques have significantly enhanced the capability of these simulations, providing ever more realistic glimpses into the cosmic past. Observing cosmic filaments and voids presents several significant challenges, primarily due to their scale faintness and the limitations of our observational tools. Cosmic filaments stretch over hundreds of millions of light years, making them incredibly difficult to observe in their entirety. Their immense size means that they often appear very dim, as the light from the galaxies that populate them is spread over vast distances, leading to challenges in detecting and analyzing them. This faintness requires astronomers to use highly sensitive instruments, and even then the data collected can be sparse, necessitating extensive computational methods to piece together a coherent image. Moreover, cosmic voids pose unique observational hurdles. These voids are not completely empty. They are characterized by a lower density of galaxies, which means that the light from these regions is much less intense. Consequently, identifying and studying voids demands advanced techniques, such as large-scale surveys that can map out the distribution of galaxies. However, the sheer volume of data generated in such surveys can be overwhelming, leading to challenges in interpretation and understanding. Another significant challenge is the influence of the intergalactic medium, the matter that exists in the space between galaxies. The presence of gas dust and cosmic rays can distort our view, making it difficult to obtain a clear picture of their true structure and composition. Furthermore, the vast distances involved mean that we are often observing them as they were in the distant past, complicating our understanding of their current state and evolution. Technological limitations also play a critical role in these challenges. While advancements in telescopes and imaging techniques have improved our ability to observe, the current generation of instruments still struggles with the resolution and sensitivity needed. Observatories like the Hubble Space Telescope and the James Webb Space Telescope provide unprecedented views, yet their capabilities are still constrained by the laws of physics, and they often require long exposure times to capture sufficient light. Additionally, the increasing sophistication of data analysis techniques is helping, but the sheer complexity of the universe means there is always more to learn. Cosmic filaments play a significant role in the overall gravitational lensing effect, and understanding this contribution reveals fascinating aspects of cosmic structure. These filaments are part of the large-scale structure of the universe, forming the backbone of galaxy clusters and superclusters. They can stretch across hundreds of millions of light years, creating a web-like pattern that connects galaxies and galaxy groups. When light from distant objects travels through the universe, it encounters these cosmic filaments, which, due to their mass, exert a gravitational pull on the light, bending its path. This bending of light is what we refer to as gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. In particular, the gravitational lensing effect is enhanced by the concentration of mass. As the more massive a structure is, the stronger its gravitational influence. Therefore, when light passes near a cosmic filament, the interaction can lead to multiple images of the same distant object, or even create arcs and rings known as Einstein rings, which are spectacular visual phenomena, resulting from the alignment of the source lens and observer. The alignment is crucial. The degree of lensing depends on how precisely the light aligns with the mass of the filament. Additionally, cosmic filaments can amplify the light from distant galaxies, making them easier to detect, especially in surveys aimed at studying the early universe. This amplification occurs because the gravitational field of the filament acts like a lens, focusing the light. As a result, astronomers can study objects that would otherwise be too faint to see, providing valuable insights into the formation and evolution of galaxies. Observations of these filaments can also help scientists understand the distribution of dark matter, which is not directly observable but manifests its presence through gravitational effects. Researchers utilize advanced telescopes and imaging techniques to observe these effects, allowing them to map the underlying structure of the universe with greater precision. By analyzing the lensing patterns, astronomers can infer the mass distribution of the filaments and the surrounding matter, which is critical for understanding the cosmic web's role in galaxy formation. Recent studies have shown that the interplay between cosmic filaments and the galaxies within them can lead to complex dynamics, influencing star formation rates and the evolution of galactic structures. The impact of cosmic structure on the large-scale cosmic flow of matter is a fascinating topic. It involves understanding how galaxies and clusters influence the movement of matter. Cosmic structure, which includes everything from filaments of dark matter to empty voids, plays a critical role in shaping the flow of matter on a grand scale. The distribution of mass in the universe, particularly the gravitational pull from these structures, guides the motion of galaxies and clusters as they move through the cosmic web. This cosmic web is made up of a network of galaxies and intergalactic gas. It creates a sort of highway for matter to flow along, influenced by gravity. As matter flows through this web, it tends to gather in denser regions, leading to the formation of galaxy clusters, while less dense areas become voids. The movement of matter is not uniform. Instead, it is affected by the gravitational interactions between these structures. For instance, when galaxies pass close to one another, they can experience gravitational influences that alter their trajectories, pulling them closer together or pushing them apart, which can lead to collisions or mergers over billions of years. Furthermore, the large-scale flow of matter is also impacted by the expansion of the universe, which causes distant galaxies to move away from us. But this expansion interacts with the attractive force of gravity, creating a delicate balance between the two forces. The cosmic flow is also influenced by dark matter, which, although invisible, makes up a significant portion of the universe's mass. Dark matter forms a scaffold that holds galaxies and clusters together, and its gravitational effects can accelerate the flow of visible matter, shaping the structure of the universe as we know it. Observations show that matter flows along the filaments of the cosmic web, and this flow can be traced using advanced techniques such as redshift surveys and gravitational lensing, allowing astronomers to map out the distribution of matter across vast distances. Understanding how cosmic structure impacts the large-scale flow of matter is crucial for studying the evolution of the universe, as it helps scientists uncover the processes that led to the formation of galaxies. Moreover, this knowledge also aids in our comprehension of cosmic phenomena, such as gravitational waves, and how they interact with the matter flowing through the universe. As researchers continue to explore these connections, they are piecing together an intricate puzzle. Cosmic voids are fascinating structures in the universe, representing vast empty spaces that exist between galaxies and clusters of galaxies. They play a significant role in shaping the large-scale structure of the cosmos. When we talk about isotropy, we're referring to the uniformity of the universe. When viewed from different directions, the cosmic microwave background radiation appears almost uniform, suggesting that on a grand scale, the universe looks similar, regardless of the direction in which we look. How do cosmic voids contribute to this isotropy? First, it is essential to understand that the universe is not filled uniformly with matter. Instead, it has a complicated web-like structure, where galaxies are found in filaments and clusters, while voids are the sparse regions in between. These voids, despite being empty, influence the gravitational dynamics of the surrounding matter. The presence of voids leads to lower densities of matter in those regions, which in turn affects how gravity operates on the scales of galaxies and larger structures. As galaxies and clusters move in response to gravitational forces, they tend to be influenced by the nearby matter, and the voids create an area where there is a significant lack of mass. This lack of mass means that light traveling through these regions experiences less gravitational lensing, allowing for a more uniform distribution of light across the universe. Essentially, the voids act as a sort of buffer, smoothing out the gravitational influences from denser regions, which helps maintain the isotropy observed in the cosmic microwave background. Furthermore, the dynamics of cosmic expansion are also affected by these voids. As the universe expands, the gravitational pull of the surrounding matter and the voids themselves influence the motion of galaxies. In voids, galaxies are less likely to cluster tightly together, which leads to a more homogeneous distribution of galaxies in the void regions. Compared to denser areas, this relative uniformity can contribute to the overall isotropic nature of the universe. It is also worth noting that simulations and models of the universe, which incorporate the effects of cosmic voids, show that they can lead to a more isotropic distribution of large-scale structures. The voids help to counterbalance the effects of overdensities found in clusters and filaments, promoting a more uniform appearance when viewed from different angles. Thus, while the universe is lumpy up close from a great distance, it appears smooth. The Sloan Digital Sky Survey, or SDSS, has had a monumental impact on our understanding of the universe, particularly when it comes to studying cosmic filaments, the vast thread-like structures that form the backbone of the cosmic web. Launched in 2000, SDSS has utilized advanced imaging and spectroscopic techniques to map approximately a quarter of the sky, gathering data on millions of galaxies and quasars. This extensive survey has provided astronomers with a treasure trove of information that helps to illuminate the distribution of matter in the universe, which is critical for understanding the nature and evolution of these cosmic filaments. One of the key contributions of SDSS is its ability to measure the redshift of galaxies, which indicates how fast they are moving away from us. Due to the expansion of the universe, by analyzing the redshifts of galaxies, researchers can trace the large-scale structure of the universe and identify how cosmic filaments influence the motion of galaxies within them. This is crucial as the gravitational pull of these filaments affects galaxy formation. Furthermore, the data from SDSS has enabled scientists to study the density of dark matter, which plays a vital role in the formation of these filaments, acting as the scaffolding around which visible matter gathers. In addition, SDSS has facilitated the study of the intergalactic medium, the gas that fills the space between galaxies. These fluctuations are essential for understanding how cosmic filaments evolve over time, as they can influence star formation rates in nearby galaxies. The survey's comprehensive catalogue of galaxies and their properties allows researchers to analyze things, how these filaments act as conduits for gas and energy, fostering an environment conducive to star formation in some regions, while suppressing it in others. Moreover, the survey has provided insights into the role of environment in galaxy evolution. By examining how galaxies are distributed along cosmic filaments, scientists have discovered that those located in denser regions tend to have different characteristics compared to those found in more isolated areas. This environmental dependence is crucial for understanding why some galaxies evolve into massive ellipticals, while others remain smaller and more irregular. The SDSS also plays a crucial role in advancing the field of cosmology. By mapping the large-scale structure of the universe, it aids in testing theories of cosmic evolution, including the role of dark energy and the validity of the standard cosmological model. Researchers differentiate between filaments and other cosmic structures through a combination of methods: observational techniques, theoretical modeling, and advanced simulations. Filaments are essentially the threads of the cosmic web, where galaxies, dark matter, and gas are interconnected. To identify these filaments, astronomers often rely on large-scale surveys of the sky. By analyzing the distribution of galaxies and the gas that emits light, they can map out the structure of the universe and highlight the areas where filaments are located. One key method involves looking at the density of galaxies. Filaments typically have a higher concentration of galaxies compared to voids. Researchers use statistical analysis measuring how galaxies are spaced apart to identify areas that have more galaxies clustered together, indicating the presence of a filament. Additionally, the alignment of galaxies can provide clues, as galaxies in filaments often align along the same direction, revealing the underlying structure connecting them. Another important aspect is the study of intergalactic gas. Filaments often contain hot, diffuse gas that can be detected through different forms of radiation, such as X-rays or emissions from hydrogen. By using spectroscopy, scientists can analyze the light from this gas, determining its composition and temperature, which helps distinguish filaments from other structures like galaxy clusters. Furthermore, researchers use computer simulations to model the evolution of the universe. These simulations allow scientists to predict how filaments should look based on the initial conditions of the universe. By comparing these simulations with observational data, researchers can refine their understanding of what filaments are and how they differ from other cosmic formations. In addition to these techniques, gravitational lensing provides another tool. When light from distant galaxies passes through a massive structure like a filament, it bends due to gravity, creating distortions in the image we see. By analyzing these distortions, researchers can infer the presence of filaments and their mass, helping to differentiate them from other structures in the cosmos. Moreover, advancements in technology have played a significant role. More sensitive detectors and faster computing power have enhanced our ability to detect filaments. As telescopes become more sophisticated, the resolution of the images they capture improves, allowing for more detailed studies of these cosmic structures. Cosmic filaments are massive structures that form the backbone of the universe's large-scale structure. They are part of what is often referred to as the cosmic web, which looks like a vast network of threads stretching across the universe, connecting clusters of galaxies. The relationship between cosmic filaments and the formation of galaxy clusters is significant, as these filaments play a crucial role in the processes that lead to their assembly and growth. Essentially, cosmic filaments act as highways for matter, facilitating the flow of gas and galaxies toward the denser regions of the universe, where galaxy clusters eventually form. As matter moves along these filaments, it is drawn together by gravitational attraction, causing regions of higher density to emerge. This process is known as gravitational collapse, where the gravitational pull of the mass within the filaments causes gas and dark matter to clump. Over time, these denser regions attract more matter, leading to the formation of galaxy clusters. The gas within the filaments can also cool and condense, contributing to star formation in galaxies that eventually populate the clusters. Furthermore, the cosmic filaments are hot and contain a significant amount of diffuse gas, which can become part of the clusters as it cools. The interplay between the hot gas and the gravitational forces within the filaments influences the dynamics of cluster formation. As clusters form, they can merge, which may lead to the growth of even larger structures. This merging process also contributes to the complex interactions that take place, affecting the distribution of galaxies and the overall evolution of the universe. The study of cosmic filaments and their relationship with galaxy clusters provides important insights into the large-scale structure of the universe. Researchers utilize advanced observational techniques to map the cosmic web and understand how these filaments influence the growth of galaxy clusters. Observations from telescopes have provided valuable data that help in piecing together the puzzle of how these cosmic structures are interconnected. In recent years, scientists have also been exploring the role of dark matter in this process. Dark matter is believed to be concentrated along the cosmic filaments, enhancing their gravitational pull and aiding in the formation of structures like galaxy clusters. This interplay is fundamental to our modern understanding of cosmology. Cosmic voids are vast, empty spaces in the universe, and they play a significant role in the overall cosmic star formation rate. These voids, which make up about 80% of the universe's volume, are areas where the density of matter is much lower than in surrounding regions. This lack of matter means that there are fewer galaxies and stars, creating an environment that is quite different from denser regions. The influence of cosmic voids on star formation is primarily linked to gravitational dynamics. In denser regions, gravity pulls matter together, leading to the formation of galaxies and stars, while in voids, the weaker gravitational pull results in less matter available for star formation. Additionally, cosmic voids can affect the flow of gas and dark matter. These voids can act as barriers, redirecting the movement of gas that is essential for star formation. When gas clouds encounter a void, they may be stripped of their material or pushed outwards, preventing them from collapsing under their own gravity to form stars. This process can significantly reduce the star formation rate in these regions. Furthermore, the presence of voids influences the surrounding areas. By altering the gravitational landscape, structures in the universe such as filaments and walls of galaxies are often found adjacent to these voids, and the interactions between these structures can enhance or inhibit star formation. Surprisingly, some studies suggest that voids may also play a role in the evolution of galaxies. Galaxies that lie on the edges of voids can experience different environmental conditions, leading to unique evolutionary paths. In particular, the lower density in voids can result in less frequent interactions, which can affect their growth and the rate at which they form new stars. This leads to a more isolated environment, where galaxies might retain their gas longer, allowing for possible bursts of star formation under certain conditions. Moreover, the cosmic microwave background radiation shows variations that correspond with the distribution of matter in the universe, including voids. These fluctuations can indirectly influence the cooling rates of gas in voids, affecting the ability of that gas to collapse into stars. The interplay between the radiation from the early universe and the structure of cosmic voids is an active area of research. The existence of cold, dark matter is supported by various lines of evidence, particularly the large-scale structure of the universe, which includes filaments and voids. One key piece of evidence comes from the way galaxies are distributed across the cosmos. When astronomers map the locations of galaxies, they find that they are not randomly scattered, but instead they form a web-like structure. This cosmic web consists of dense regions known as filaments, where galaxies are clustered together, and vast empty regions known as voids. The presence of these filaments and voids can be explained by the gravitational effects of cold dark matter. Simulations of the universe's evolution show that as the universe expands and cools, matter begins to clump together under the influence of gravity. This clumping leads to the formation of filaments, where the density of matter is high, while the voids represent areas where the gravitational pull is weaker. These simulations closely match the observed structures in the universe, providing strong support for the cold dark matter hypothesis. Furthermore, studies of gravitational lensing provide additional evidence. When astronomers observe gravitational lensing around galaxy clusters, they find that the amount of lensing is greater than what would be expected. From the visible matter alone, this discrepancy suggests that there is additional mass present, consistent with the presence of cold dark matter. Additionally, observations of the cosmic microwave background also support the model. The CMB is the remnant radiation from the Big Bang. Its temperature fluctuations provide a snapshot of the early universe. Detailed measurements of these fluctuations indicate that the universe is composed of about 27% dark matter. With cold dark matter being the primary component, the patterns observed in the CMB align with predictions made by models that include cold dark matter, further reinforcing its existence. In summary, the distribution of galaxies into filaments and voids, the effects of gravitational lensing that reveal unseen mass, and the detailed measurements of the cosmic microwave background all point towards the crucial role of cold dark matter in shaping our universe. Baryon acoustic oscillations are a fascinating phenomenon, closely tied to the formation of cosmic structures. To understand this relationship, we first need to explore what they are. They originated in the early universe, when matter and radiation were in a hot, dense state. During this time, sound waves traveled through the primordial plasma, creating regions of higher and lower density. As the universe expanded and cooled, these oscillations imprinted themselves onto the distribution of matter, eventually leading to the large-scale structure we observe today. These oscillations are the result of interactions between baryonic matter and photons. When the universe was just a few 100,000 years old, it was still hot enough for photons to scatter off baryons frequently. This scattering created pressure waves, which moved through the plasma, creating a series of compressions and rarefactions. Much like sound waves in air, as the universe continued to expand, it cooled down, allowing protons and electrons to combine and form neutral hydrogen, a process known as recombination. At this point, the photons could travel freely through space, and the sound waves were essentially frozen into the density fluctuations they had created. These density fluctuations, now encoded in the cosmic microwave background, led to the formation of structures like galaxies and galaxy clusters. When we look at the distribution of galaxies today, we can see that they are not randomly spread out. Instead, they form patterns with certain distances between them that reflect these early acoustic oscillations. Researchers have found that the typical separation between galaxies is about 500 million light-years, a distance that corresponds to the scale of these oscillations, known as the baryon acoustic scale. The study of baryon acoustic oscillations has become an important tool in cosmology. By measuring the distribution of galaxies, scientists can infer details about the universe's expansion history, its geometry, and the amount of dark energy present. The patterns left by these oscillations serve as a cosmic ruler, helping astronomers to understand how fast the universe is expanding and what its fate might be. Observations from projects like the Sloan Digital Sky Survey have provided valuable data. that supports the existence of these oscillations and their role in cosmic structure formation. Furthermore, baryon acoustic oscillations are not just relics of the early universe. They continue to influence the evolution of structures in the cosmos today. As galaxies form and grow through mergers and accretion, cosmic voids play a significant role in our understanding of cosmic structure, particularly when considering theories of gravity that go beyond Einstein's general relativity. These voids can be seen as a unique laboratory for testing the limits of our current theories, as well as exploring alternative models. In the framework of general relativity, gravity is understood as the curvature of space-time, and while this model has been immensely successful, cosmic voids present intriguing challenges. One of the implications of cosmic voids is their influence on the distribution of matter and the dynamics of cosmic expansion. In regions of low density such as voids, the expected gravitational effects may differ from those predicted by general relativity. For instance, some modified gravity theories suggest that gravitational behavior in these environments could lead to different observable effects, such as altered galaxy motions or variations in the cosmic microwave background patterns. These deviations from expected behavior could help scientists identify the presence of new gravitational forces or interactions not accounted for by general relativity. Moreover, cosmic voids can serve as a testing ground for concepts like dark energy, the way galaxies are distributed around voids, and how they interact with the surrounding cosmological fabric, can reveal information about the nature of dark energy and its relationship with gravity. Some theories propose that modifications to gravity could mimic the effects of dark energy, leading to a complex interplay between these two phenomena. Understanding how voids influence the dynamics of cosmic expansion could provide insights into whether we need to revise our theories of gravity. In addition to their implications for gravity, cosmic voids also challenge our understanding of structure formation. Standard models based on general relativity predict that matter should clump together, leading to the formation of galaxies and clusters. However, the existence of large voids suggests that there are additional forces or processes at play, which might be better described by alternative theories of gravity. For example, some researchers are investigating how modifications to gravity could account for the observed underdensity in voids, potentially linking these observations to a broader framework of cosmological evolution. The study of cosmic voids also raises questions about the overall homogeneity of the universe. The distribution of cosmic filaments is influenced by a variety of factors, including the expansion of the universe and gravitational interactions. Over time, as the universe expands, cosmic filaments evolve, with their shapes and densities changing significantly. Initially, in the early universe, matter was distributed more uniformly, but as gravity began to pull matter together, regions of higher density formed, leading to the development of these intricate filaments. These structures are part of what is known as the cosmic web, a large-scale structure where filaments connect clusters of galaxies, and voids exist between them. As the universe continues to expand, the dynamics of these filaments shift. The gravitational attraction between the matter in the filaments causes them to grow thicker and more pronounced over time, while regions that are less dense may become even emptier. Additionally, mergers between galaxies and clusters within these filaments can lead to changes, as massive structures pull surrounding matter towards them, creating new filaments and altering existing ones. This process is often referred to as hierarchical clustering, where smaller structures combine to form larger ones. It plays a crucial role in shaping the universe we see today. Furthermore, simulations of cosmic evolution reveal that the distribution of filaments is not static. It is a dynamic process influenced by dark energy as well. Dark energy is thought to drive the accelerated expansion of the universe. It affects how matter is distributed over cosmic timescales. As dark energy pushes the universe apart, it influences the growth of cosmic structures, including filaments, leading to a more complex arrangement of galaxies and dark matter over billions of years. Researchers have utilized advanced computer simulations, alongside observational data from telescopes, to study how cosmic filaments form, evolve, and interact with one another, helping to paint a clearer picture of the universe's large-scale structure. In essence, the distribution of cosmic filaments changes significantly over time due to gravitational forces, mergers, and the effects of dark energy, resulting in a constantly evolving cosmic web. The intricate dance of matter, energy, and gravity continues to create a rich tapestry, revealing the dynamic nature of our universe as it ages. The role of magnetic fields in the dynamics of cosmic filaments is both fascinating and complex. As these vast structures are fundamental components of the universe's large-scale structure, cosmic filaments are the largest known structures in the universe, composed of dark matter gas and galaxies, forming a web-like pattern that connects clusters of galaxies. Magnetic fields, which are present in the intergalactic medium, play a significant part in shaping the behavior and evolution of these filaments. They can influence the movement of charged particles, such as electrons and protons, which are prevalent in the hot gas that fills these filaments. The presence of magnetic fields can lead to the generation of currents, which in turn can affect the flow of matter along the filaments, thereby impacting cosmic structure formation. Moreover, magnetic fields can help regulate the temperature and density of the gas. For instance, they can inhibit the collapse of gas clouds, allowing the gas to remain in a more diffuse state, which is crucial for the processes that lead to star formation and galaxy evolution. Researchers have found that the strength and orientation of magnetic fields can vary across different regions of these filaments, affecting how matter accumulates and interacts within them. This variability can lead to differences in star formation rates and galaxy properties, as the magnetic environment can either promote or suppress the conditions necessary for stars to form. Additionally, studies suggest that magnetic fields may play a crucial role in cosmic ray propagation. Cosmic rays are high-energy particles originating from supernovae and other energetic events. They interact with magnetic fields, causing their paths to be deflected. This interaction can influence the distribution of cosmic rays throughout the universe, impacting the overall energy dynamics of cosmic filaments. The interplay between magnetic fields and cosmic rays can also affect the thermal balance of the intergalactic medium, which can have broader implications for our understanding of cosmic evolution. Furthermore, simulations of cosmic structure formation are increasingly incorporating magnetic fields to provide a more accurate representation of the universe's evolution. These simulations suggest that magnetic fields can enhance the clumping of matter in filaments, leading to the formation of dense regions that will eventually evolve into galaxies. As researchers continue to explore these magnetic influences, they are beginning to uncover how magnetic fields might contribute to the formation of the cosmic web itself, influencing the layout of galaxies and clusters across vast distances. In the broader context of astrophysics, understanding the role of magnetic fields is essential. Cosmic voids, those vast, empty spaces in the universe, play a significant role in the overall evolution of the universe. Understanding their impact requires delving into their formation and the dynamics of cosmic structure. When we look at the universe on the largest scales, we see that it is not uniformly distributed. Instead, it consists of a complex web of filaments and clusters, with these enormous voids in between. These voids can be thought of as the empty spaces in a cosmic sponge, a metaphor often used by astronomers to describe the large-scale structure. The formation of cosmic voids dates back to the early universe, shortly after the Big Bang. When matter began to clump together due to gravitational attraction, as matter accumulated, it formed denser regions, which would eventually become galaxies and clusters, while the less dense regions evolved into voids. This process is a fundamental aspect of cosmic evolution, as the distribution of matter influences how galaxies form and evolve over time. Voids can affect the large-scale structure of the universe in several ways. For one, they influence the motion of galaxies. Galaxies tend to move toward regions of higher density, meaning that their paths are often shaped by the gravitational pull of nearby clusters, creating a sort of cosmic dance. This gravitational interaction leads to what is known as cosmic web dynamics, where galaxies are drawn into filaments and clusters, leaving the voids relatively empty. The presence of these voids can therefore dictate the flow of galaxies, as they act like highways guiding galaxies toward denser areas. Additionally, cosmic voids contribute to the overall expansion of the universe. As the universe expands, the voids grow larger, and the dynamics within these voids can influence the rate of expansion. Dark energy, the mysterious force driving the accelerated expansion, interacts with the matter in these voids, potentially affecting how structures evolve over cosmic time. The expansion of voids can also result in a phenomenon known as cosmic acceleration, where the growth of these empty regions leads to changes in the gravitational dynamics of surrounding structures. Moreover, voids can affect the properties of the cosmic microwave background radiation, the afterglow of the Big Bang. The presence of voids can create temperature fluctuations in this background radiation, as the density of matter influences how light from the early universe travels to us.